All right, here's another problem. So this one is from chapter 7, problem number 25. It says that a 100-kilogram block in the figure takes 6 seconds to reach the floor after being released from rest. What is the mass of the block on the left? The pulley is massless and frictionless. So notice that the 100-kilogram block is 1 meter above the ground, and the problem says that it's going to take an amount of time equal to 6 seconds to reach the ground. So you got some information there about distance and time that it took the block to move that distance, and they're asking about the mass of this guy over here. What is the mass of the block? So this in this setup, this block is going to go down and the mass m is going to go up. So the idea would be to use the distance and the time information to figure out the acceleration of the 100-kilogram block. Knowing the acceleration of that block, we know what's the acceleration of the other block, of the m, lowercase m, and knowing the acceleration of that block and having the we can set it up with the Newton's second law in the vertical direction for the tension minus the weight and make it equal to the mass times the acceleration, and we should be able to solve from there, from that equation. So let's take a look. So let's start with what I said at the beginning. So we're going to calculate the acceleration. So delta y here, the distance traveled by the 100-kilogram block, is going to be the initial velocity of that block multiplied by time plus 1/2 of the acceleration times the time squared. Now the block is released from rest. It is released from rest. So that's a 0 right there. We know that the distance that the block is going to travel is 1 meter. So we can make 1 meter, well, if you want to be careful about this with the minus sign, you would say that delta y is going to be minus 1 meter. So minus 1 meter equals 1/2 of the acceleration, and the time is 6 seconds. So 6 seconds square. So the acceleration is going to be negative 2 meters divided by 36 centimeters squared. And that gives you 1/18 meters per second square, and negative. So negative because the 100-kilogram block is going down. All right. I think I would like to calculate the tension in the string also. Before we move on to the lowercase m block, I would like to calculate what's the tension in the rope. So let's take a look at the 100-kilogram block and see what's going on with that one in terms of the forces. So for that block, we have the tension and we have the weight, which is mg, and we know that the acceleration is going to be in this direction, and we know how much the acceleration is. So according to Newton's second law, we're going to have that the tension minus the mass of that block, which is 100 kilograms times 9.8 meters per second square, T minus mg, those are the two vertical forces. Sum of them equals mass 100 kilograms times the acceleration, which is minus 1/18 meters per second square. Let me erase here. Minus 1/18. All right, so from this equation, I'm going to calculate the tension. So the tension in the string is going to be 100 times 9.8 is 980. That will be newtons. Plus, but with a minus, just minus 100 divided by 18. And again, kilograms meters per second square is the same as newtons. So the final answer for the tension is going to be, let's put it in the calculator. So let's see, 100 divided by 18 is 100 divided by 18 is 5.55. So this is 980 minus 5.55. So the final answer for the tension is going to be 974.45 newtons. All right. So far we managed to calculate what's the acceleration of the 100 kilogram block. We calculated the tension in the string that is touching that block. Now it's time to move to the lowercase m and see what we can figure out analyzing that object. So the lowercase m block, it's going to be accelerating upwards. The constraint equation for this system is that acceleration of block 1 equals the negative of the acceleration of block 2. This was discussed in the videos about Atwood's machine. So the acceleration of the lowercase m, we write it as a sub m, is going to be simply positive 1 over 18. 1 over 18 meters per second square. Now, if we look at the forces acting on that object, and why wouldn't you look at the forces if this is a Newton's second law problem? So the forces acting on that object are the tension, of course, going up, lowercase m times g going down. So tension up minus the weight, mg, that's the two forces that are acting in the vertical direction. There's no other forces, equals lowercase m times the acceleration. So in this equation, do we know the acceleration? Yes. Do we know the mass of the block? We don't know the mass of the block. In fact, that is what they're asking us. That's the one question of this problem, is what is the mass of the block on the left? So m is not known, but do I know the tension, this T? The answer is yes. We just did that in the down here. We figure out that the tension on the string that is pulling on the 100 kilogram block is 974.45 newtons. That is exactly, so that was this tension. Well, that is the same as this tension. In the videos where we discuss strings and pulleys and stuff like that, we said that the tension along a massless string is the same everywhere. So the string pulls on both sides. Whatever object is connected to the two ends of the rope is going to be pulling with the same force on each object. So those tensions are equal. So yes, we know the tension is 974.45. We have 974.45 newtons minus mg equals ma. Again, remember that we're looking for the mass, so we're going to put everything that has a mass together. So 974.45 newtons equals mass factor of g is 9.8 and the acceleration is 1 over 18. So the mass will be 974.4 divided by, what is 9.8 plus 1 over 18? So let's do that. 1 divided by 18 is 0.0555 plus 9.8 equals 9.855. So we're dividing by 9.855. 9.855. All right, so final answer for the mass is multiplied by 974.4. 98.86. 98.86. 98.9. Let's round it to three significant figures. 98.9 kilograms. So pretty close to the mass of the 100 kilogram. And that kind of makes sense because if you think about it, this acceleration is really tiny. 1 over 18, 0.0 something meters per second square. So for the acceleration to be so small, the masses of the two objects need to be pretty close. If the masses were identical, then of course there will be zero acceleration. But if one mass is just slightly heavier than the other one, then you have a small acceleration, and that's what we have in this problem. To take 6 seconds to fall a distance of 1 meter, which is 3 feet, you can try to visualize that. It's a pretty small acceleration what we have here. So not surprisingly, the mass, the two masses are pretty close in value. So all right, let's leave it there.